Thank you. So this is the final talk. So I could do whatever complicated thing and just escape. And so that's something today's stuff. And key point is that I want to estimate this number dimension, and actually this is bounded by you make a one-time Tate twist, making a tensor product with cyclotomic character, and then actually I will estimate this by 1 under some assumption hypothesis. This type of equality, you have some representation, and it's dual. This is self-dual and bond-like dual, and then you twist by Tate. And this is called Spiegelungssatz. It was invented by Leopold in the one-dimensional case, and Iwasawa essentially used this kind of things to do his business. And this is the Greenberg-Wiles type Spiegelungssatz. In English, it is a reflection theorem. But reflection doesn't reflect. I mean, it's an inequality. Okay, so that's how things go. So I need a lot of things from local class field theory. So the local class field theory, I just summarize it. Of course, most of number theories knows, but I just use it, so I would explain it. So the K is a finite extension of QL, the erratic field. Okay, so these are Galois group of this absolute Galois group of this one, and it has an inertia subgroup. Okay, and so first thing is something Artin symbol. The X goes to, this is in K cross. I write X, K, something like that. It is from K cross injection to D, abelianization. So this is a quotient by topological commutator subgroup. And this is as a dense image. And I write K, and inside you have a uniformizer. So it generates the maximal ideal, its variation ring. And this abelianization contains, of course, the inertia group, but that is not abelianization, the image of this guy in it. So it is, I put up below. Okay? And then second thing is perhaps this pi K modulo inertia is the Frobenius element. Okay. It doesn't matter because so if you are arithmetician, you just take arithmetic. If you are direct geometer, take geometric. Then by Artin symbol, this I would use later, so I would keep it here. K cross tensor Z over some integer mz z. So this is by definition K cross modulo K cross to this integer, positive integer m. And because this is having a dense image, this Artin symbol, so this is actually the ab modulo m d ab. Okay, so this is by Artin symbol. this way. Okay? And another point is that this O cross by Artin symbol isomorphically goes to I up. So this side, inertia part is isomorphism. Okay. And now I need to have something about local cohomology. And this kind of class field theory is made out of this invariant map. That is, you take H2 of this Galois group, absolute Galois group D. When I write a cohomology of D, I just put K in it. So if I write K, K is not a group, but this is a base field, and I've taken Galois cohomology for the algebraic closure. This is very typical notation. And then you plug in mu m, mth roots of unity. I mean, as a Galois group module, you evaluate so all mth roots of unity, you have a Galois action. And then this is canonically isomorphic to Z over mz. This is a base of the homological proof of class field theory. And originally it is from the Brouwer group. Brouwer considered the Brouwer group, the classifying the central simple algebras over K, and it is a group like that up to isomorphism and up to equivalence by tensor product kind of thing. So this is something like that. Okay, so in particular, and the second thing is that this is a Kummer theory, K mu m. I just write mu m for this one, but this is not a this Galois module you pick. And then this is isomorphic to K cross over K cross to the m. So this one. So sometimes I write just with tensor product. And then this is d-ab over m d-ab. And obviously this is a dual of home d z over mz, right, by definition. And this is, if you like, it is h1k constant coefficients. This is a very basic example of Tate duality. So say you have a Galois module, say finite Galois module, C over mz, you take a group ring module. M, you pick just this one. And suppose that the size of M is finite. And then, you know, you just define the Tate dual just by form of M mu M. So this, you have a Galois action here, you have a Galois action here. So it's the Galois action of this F, sigma F x is defined by sigma acting on this roots of unity, and then sigma inverse x. So this is the action. So this is the Galois module. Then obviously the M star 1 tensor M z over mz. You pick phi, it's a homomorphism, tensor x, and you bring with phi x, that is mu m, and that induces by cup product hr. When it is obvious that the k is, I even don't write the k. Okay, so it is a k cohomology, but I just write m star 1 times h2 minus r. M goes to h2 of mu m, and that is z over mz by invariant map. So this is the pairing, Tate pairing, and the theorem of Tate is homological dimension of D is 2, and this pairing is perfect. So it's a Pontryagin dual it gives of cohomology group. So this is a well-known fact, and I have already said that this is plainly perfect dual, and basically you restrict M to kill the action and use this, come back. That's the key point. Proof is quite easy. Once you come up the idea first, usually proof is easy and you will be famous. If you follow, proof is difficult, and after some years people forget about it. Okay, so here's some example of local Tate duality. So I have a lemma. Maybe I write this here. So before really stating the lemma, that if M D acts on M trivially, so it's basically M is something like Z over M1Z times Z over MRZ. MI is a divisor of M kind of thing. Okay? No action. So that's we know the Tate duality without any proof, just by local class field theory. And under this hypothesis, the home of the Frobenius element generates the Galois group of maximal unramified extension. So Galois group of maximal unramified extension is the biggest cyclic group, so the Frobenius to the Z hat. And then you take a homomorphism into it, continuous homomorphism. Then obviously this is inside the home of the M, but that is H1M. All right. So lemma is that by Tate duality, you take M pop, the orthogonal complement. This will be the dual guy, M star 1, homology of M star 1, right? And so this guy, you can identify this by Kumar theory here inside K cross tensor over Z over MZ. No, M. Z over M, something like that. Z, I'm sorry. Right? And this is given by its integer ring tensor Z over M. This always an integer ring. So one remark is that if, for example, the P doesn't divide M, then this isomorphism is given by just you have alpha here, you take mth root of alpha, and then Galois action sigma minus 1, you move by sigma and divide by mth roots of alpha, then obviously you get a function of sigma having values in um, and that is the co-cycle. You check the co-cycle relation. And that gives the isomorphism. So if M is prime to P, the mth root of alpha generate a ramified extension if alpha is in unit, right? So if Pm, then the orthogonal complement of the unramified co-cycle here is again unramified. But for P, that's a different story. Okay, the proof is easy. Just let me do it instantaneously. So, of course, M is something like that. You can assume that M is Z over MZ, and therefore hom of D over I Z over MZ goes into hom of D Z over MZ, goes out surjectively hom I Z over MZ. The exact sequence I goes into D goes down to from Z hat. Once abelianized, this is free module over Z hat, so it's split. So this is exact. Okay, so you just write down the diagram O cross tensor Z over MZ goes into K cross tensor Z over MZ, goes down to log Z hat over log MZ hat surjectively, and this is isomorphic to H1 D over I Z over MZ dual, as I explained there, and this is isomorphic to H1 K Z over MZ dual by Tate, and therefore this is isomorphic to H1 I Z over MZ, goes into it dual, and so therefore this guy and that guy is also another complementation. And all right, so I define this dual Selma group. Actually, this dual Selma group is not identically defined by SL, so I usually put this is pop here. So why pop? Okay, so I erase, everybody saw it, I erase this stupid proof. So the definition Selma pop of add. So I just write add bar for add row bar, add bar 1, add bar Tate twist once, So add row 1, okay? And so add row bar is definition is just a kernel. Now I take, you remember that I started F cusp form, right? Actually, essentially, this K is 1, and N is those prime ramifying in your Galois representation attached to F, right? The Galois representation is R, that is compatible system indexed by that, and the ramification prime is those of N and this P. And I just write S to be those L dividing N and P and infinity. So the set of primes. And I need to actually use, so I defined the original Selma group using some Galois extension, something like Q F rho bar, the splitting field, and F P rho bar, something like that. This is only P ramified, P profinite. Right? The deformation is just that you are moving just by P. So once you go up here, the deformation Galois image is P profinite, so it is okay for the deformation thing. But this is also good. If I use this Galois group, I don't need to say anything about unramified at L or something like that kind of condition. So that's very useful to define Selma group. But once you make a dual applied and something like that, it could get out of it. So I just do it slightly generally. So I just write QS over Q maximal extension and ramified outside S. That S. Okay? So and this is good because if you do this for prime in S, you can use state duality because local Galois group under this condition, local group, particularly inertial group here, is just at L like this is finite because it's only P ramified thing. Then, of course, state duality doesn't work. And so I need to use state duality. So I actually need to write it down, the original Selma group, in this kind of way, and you can easily do that. So I don't do that. So it is Galois group of Q, Galois group of Q over QS over Q. Strictly speaking, I need to put gal here, but it is a kind of common use that you just write this, then this you have gal symbol here. Then add bar 1 to H1 QP, add bar 1 and F plus minus H1 QP, add row bar pop. Okay? This is a subspace of this guy, so you can take add row, add row, add bar pop, get into this dual guy, right? I mean, add times add goes to F. This is a matrix. Trace 0 goes to trace XY is perfect dual. So it's a self-dual. So I don't need to put a star. It's just twisting once enough when P is odd. No? When P is 2, not true. And that made the proof of Sayers mode P modularity conjecture so hard for 2. So 2 is a king of prime. You see immediately anyway. And what I'm saying is this, is that I had a deformation factor D, and you plug in F epsilon, then you get this one. Okay, so I can F epsilon, but this deformation factor I only localize at P. The same condition, ordinary condition only you import, but you do deformation over local Galois group of QP bar over QP. Then this comes out. The reason of this is just because this. And therefore, I could put this L in S, DD. You do the same thing and you plug in L here, and you put them here. And that's the definition of the dual Selma group. However, to make things easy, I just write it this one. The outcome is something like that. Strictly speaking, slightly a problem, but this guy is bigger than the one really virus defined, possibly. So to make estimate, it's fine for me. Yeah, so I'm slightly cheating. Okay, so that's the dual Selma group. So this reflection theorem dimension F of Selma adbar So this is proof uses a lot of local and global Tate duality and a Euler characteristic formula of Tate duality, and it's very long, so I don't do that. But for example, if you have enough courage, you just read the middle of the Weier's 150-page paper of proving Fermat's theorem, and if you don't like to do it, then there's my book. So I'm just Cambridge University Press, modular form and Galois cohomology proposition. So you can see the proof. It's not so hard, but if I do it, then I exhaust all the time. So that's something I admit. Okay, so I just keep this guy here. So this is due to virus Greenberg. Greenberg often do this for characteristic zero coefficients, not the p coefficients. And in that case, you often come up the equality, so that's the thing. But anyway, this is possible to have real strict inequality. Okay. Then, first of all, so I take F, the splitting field of adbar. Yes, it's a finite extension. So the point here is that you want to have a restriction map from cohomology over, say, QS over Q question to H1 QS over Q adbar, something like that, or adbar 1, maybe question mark. Okay, so I want to shift over F. I'm sorry. Restriction map. And I would work here because once I restrict it here, other disappears over F. The add is trivial, so just a Z, or I mean F cube, and add 1 is just a mu p tensor F cube, right? So it's really, I can use Kummer theory. And using Kummer theory, I try to compute the image of this Selma group, plug in question mark, this kind of thing. And so I need to know this is injective, right? So the kernel of here is, as you know, is inflation restriction to H1 of F over Q of question mark fixed by Galois group over F, right? So this has to be 0, but this is a finite group. So either I assume that, so I just write G for Galois group of F over Q. So they assume P doesn't divide order of G, or F mu P is different from F because I twisted by 1. So if cyclotomic character is non-trivial modulo P, of course the fixed point is just disappears. So that tells you the things are injected. If this side is prime to P and this is a characteristic P vector space, it also kills. And in the modular form case, this is mostly true, and this is true for weight 1 for finite, because in the weight 1 case, rho bar comes from Artin representation R, and this has already finite image, right? So therefore, excluding finitely many primes, it's okay. So that's mostly true. So that means under this kind of condition, this implies that Hj of Fq of add bar 1 of Galois group of Q bar over F is 0. Okay, so J1, 2. So actually, under this condition, you need to fix the Gal F bar over F here, then it is isomorphism by inflation restriction. Then by this inflation restriction thing, I would perhaps write inflation restriction, the H1 Q of add, I don't need to put QS here, but add bar 1 is isomorphic to F cross tensor Z add bar, right? And then you need to take the invariant under G, because this is fixed by R. This is not F over Q, TG. So you get this. This is diagonally you let it out. Okay, so this is, I possibly write this F cross tensor F over Z of isotypical component of add. It's not, add may not be irreducible. So strictly speaking, you can also perhaps better say kind of way. If original law is induced representation, perhaps I have already said that if R is induced from some quadratic field to Q of character phi, then add will be this quadratic d over something tensor direct sum of induced of the same field of another character I wrote phi minus anticyclotomic projection. So in this case, this could be just a chi component or this part component. And if further, for example, this is order 2 or something, then this further split into 2 characters, then one of them finally show up. But anyway, it doesn't matter. Okay, so that's the Kumar theory. So here's a theorem. So suppose P doesn't divide class number of F times order of G. Okay. Then and write O for the integer ring of F. There, O is a local erratic field, but now O is a global integer ring. And then Selma pop add 1, embed into O tensor, O cross tensor Z over F of a joint component. By the way, here I said the fixed part by tensor product and also home of G. I use that as is self-dual. So characteristic 2. So 2 is no good for my argument also. So that's the, you need to pay some respect towards the king. Okay, so why? So this is, okay. So I have you take Selma cocycle, dual Selma cocycle. So you restrict it to F, right? Then this is something U alpha sigma is essentially, because I have tensor F things there. If F is FP, I don't need to do anything but alpha sigma minus 1 kind of thing. It's a linear combination of this kind of thing with coefficient. So I just simplistically, I just assume this kind of way. And you conjugate this sigma under the Galois action of capital G, the Galois group of F over Q. This will move according to this add. Okay. So alpha is originally okay, so first I try to show, so the first try to show cell pop add bar 1 inside O 1 over P. I invert P cross tensor ZF add bar. This is first step, and this is almost by definition, or because my cheating, it is already alpha is unramified. So U alpha restricted now decomposition group at L is essentially it's the same thing. I mean, essentially piece root of alpha, but alpha regarded in maybe Gothic L, F Gothic L, right? Something like that, cross. But it is unramified, so it is up to P power of this element comes from unit. As I explained in the proof of the lemma, that alpha is O cross L tensor F up to FL cross to the P. I mean, this doesn't cause any trouble, right? That means you consider the principal ideal alpha of generated by this global element alpha. So alpha times O 1 over P. So this is an O 1 over P ideal, fractional ideal. Okay, so I just make a decomposition. Alpha is because of this, right? The exponent showing up here, you have some prime showing up. The prime is a prime here, no prime above P. Okay, so the L and this is a L to the sum P times EL, because up to P power, something like that. Now, so in other words, alpha is some ideal to the P. Okay, this is P. So I use the assumption here, P doesn't divide H, HF. Then you replace alpha by alpha to the H. What happens? This co-cycle will be get multiplied by H, but H is not divisible by P, so it doesn't have any real effect. So I can do that. Okay? No effect to our proof. But once you do that, this Gothic way is also raised power to the H. So strictly speaking, if you like really precise sort of formulation, I only need to assume that class number of O 1 over P is prime to P. Yeah. But P is moving later, so then it's all right. So that means alpha is A over P but this A is replaced by A to the H. So this is a principal, so you get alpha prime there. So this is alpha prime to the P. In other words, alpha is epsilon times alpha prime to the P. Therefore, you can replace, epsilon is of course unit. Can replace alpha by epsilon. So that's the claim I made this first there. So this first step done. So second step, I need to show this at P. Okay. So I just put X to be O 1 over P cross tensor Z F over O cross, this is the defect, F, and this is therefore isomorphic. You have any psi here, you associate the divisor of psi, well actually psi in it is here itself, then you get a direct sum only. So I pick P prime P dividing P, and this P, the decomposition group is D inside G. So all other primes P sigma, so G over D over G. Well, G over D, I act sigma from the right side times F. So this is induced representation as a Galois module from D to G of identity. That's a Galois module. I'm sorry, I need to raise slightly a power. A is, I mean, this is principal here. So this A is basically class number kind of things, but order of this P in the class group. Well, anyway, you get an induced representation of one. So I need to, so my Galois module I'm looking at is home of add. I use this is the module I wrote O cross tensor F add bar. Okay, so I use this formulation. All right. So whether if add doesn't show up here, it's okay, right? And so I look at that. Does show up, but not on the Selma cycle. Okay, so this end, therefore D to the G of identity, you take add component, then this is a home, G home of add bar in DG1. So by Shapiro's lemma, so this is a finite, everything finite. So induced can be right side or left side, it doesn't matter. And you remember that this add at P I assumed at the very beginning that it is epsilon bar delta bar 0 something, and epsilon bar is different from delta bar. This is unmodified ordinarity condition. So no, low. So add bar is restricted gal QP bar over QP is epsilon bar delta inverse 1 epsilon this is 0 actually, because I assumed that the ramification index even at P is prime to P. Something like that. And this is non-trivial because of that. Not equal 1. 1 epsilon. Yeah. This is inverse. This is plus. Thank you. So they are not equal 1. So the 1 shows up only once. And therefore, by Shapiro, this is F. That means the inertia action, if any, I mean, this epsilon delta both could be unramified, but I don't care. Only I need to concentrate on one case. So this cohomology group you need to look at is only concentrated on this one thing. So the middle guy, or if you write A minus A, B, C, the adjoint module, this central guy I'm looking at. And then it is just as I said, F plus minus and so on is just an orthogonal complement of original addressing that is home of D of lob to the Z. Now it is Z hat, but it is target is characteristic P, so I can put the ZP here and F. Right? The orthogonal complement of this is O P tensor F. Therefore, the cocycle is, this is not an unramified cocycle, but it is in this sense integral. So I found that it is outside P it is already integral, and at P also integral. So you win. So this I use the fact here. This fact I use. Okay, so out of you, so here I already used that P doesn't divide group order of group G and so on. So it is essentially therefore Artin representation case, because if it is higher weight, usually the Galois image contains SL2 of Fp, so the order is divisible by P. However, there's another argument that if you assume that P the ramification index of P in this F is prime to P, I mean the case where the companion form exists, then the argument actually could go through, but I don't touch on it. Okay. So using this, I try to now compute this side. So what is so I want to show that this guy is 1. Okay, so now I go infinity, please. I worked up to here at place P essentially, and now at infinity. Okay, so I study all cross, and as when Minkowski proved Dirichlet's unit theorem, infinity, I just take infinite places of F as a set. F is a complex, I mean imaginary field, so half of number of embedding, I mean embedding modulo complex conjugation. Okay, so I have a logarithm map, so it's something log of epsilon is usual Archimedean logarithm, absolute value of epsilon at Archimedean place V, and V infinity. So this is 2. Therefore, R infinity is just a product all V in infinity of R. And the Galois action is just permuting this guy. Therefore, this is induced representation now from complex conjugation, group generated by complex conjugation to Galois group. C is subgroup generated by complex conjugation. You fix one complex conjugation anyway, like I fixed Gothic P there. And again, you get this thing. All right? So after tensoring a real number, you get this essentially. So this implies because P doesn't divide order of G, so under this condition, you get the so first one step. You can descend this to Q, O cross tensor Q as a Galois module. Direct sum identity you add is by this is induced representation C to G of Q times identity representation. This is nothing I need. Then P doesn't divide G. I can descend to F. So I need to make it torsion free, so I need to, it is at most, F can have at most piece roots of unity only, P torsion, because I tensor F. This is direct sum F1 under this condition. So I use the G is now divisible by P here. Actually, well, so here's a theorem I wanted to prove that Okay, so that's the proof. Let's continue here. So, O cross tensor, I need to divide mu pf. It's just the same argument. Then this is isomorphic too, because this you can ignore it because this doesn't contain there. So by Shapiro's lemma, essentially, Shapiro's lemma, you get this form. So here's a Shapiro's lemma, I'm sorry. F1. Okay, but this is, it's an odd representation adjoint. So it is -1, 1, -1. So you have only 1, 1. So therefore this is F. So the dimension is essentially, I need to still deal with mu pf. But if there's no p roots of unity in O cross, then you win. So why mu p doesn't matter? That's an easy exercise, but as I said, I don't go into details, but for example, if f mu p is different from f, obviously it is okay, right? And this is usually the case, but if the bad case, because this is one case, if ad is irreducible, okay, because there's a one-dimensional space at most of mu p, right? But it's three-dimensional of because dimension f of mu pf is less than 1, but dimension is 3. And so reducible case, as I said, is either chi direct sum chi 1, chi 2, chi 3, 3 quadratic characters, or chi direct sum induced 5 minus kind of thing. But so this is the problem. This is irreducible by the same argument. This is all quadratic characters. But this is a roots of unity, piece roots of unity. Here I need to assume that p is bigger than 5. Then you don't have a quadratic character like that. So I win. So 3 is slightly problem. Well, I need to really, so 2 is obviously you can't do. All this argument, 2 is bad. But 3 doable, but all right. So I get a cyclicity theorem. If P doesn't divide G times HF, and of course and p bigger than 5, then for any row in D of A, the deformation factor, cell add row is generated by at most one element over A. And at the same time, I can replace in this thing by dual Selmer group. That also I bounded. And dual Selmer group also has sort of, if you define for general row, you can define dual Selmer group, and it's also kind of control theorem is okay. Okay, so that's now I assume this, suppose that now suppose that this R is local complete intersection over lambda. So this follows under Weil's condition that rho bar restricted to Q mu P is irreducible. But now, I mean, by the result of Jacton and Shekhar-Kare and Shekhar-Kare's student Kalyan Swami, Indian guy, most of case you can remove this. So usually okay, but I don't go into details, and it's still this kind of thing is developing. So I don't know at this moment what the exact condition is. So the Jacton found the idea, and so he wrote a paper. Kalyan Swami and Shekhar generalized it. And this is a good point. If somebody invented a good idea like Tate theorem, proof is easy at the beginning, then it gets hard, but you get an incremental progress, you get one paper each. Okay, so suppose this. Then this R has presentation T1, T is no good, X1, XR modulo S1, SR. And what's the minimal number of S? Minimal, of course, you can do whatever amount of number. You add one variable, you add the same variable here, you get, of course, all the time the same thing. The minimal so R to be the minimal number, then this is actually the dimension of cotangent space. So this is MR modulo MR square plus M lambda. That under this kind of assumption, I know this is less than 1. If it is 0, there's nothing to prove. You remember that Selmer group of rho Pontryagin dual is omega R over lambda. And if it is 0, R is 0, this R and lambda is the same thing. So it just vanishes, so it's okay. So I can assume R is 1. Then you have second fundamental sequence of So this means you have a presentation. Some S goes S over S goes into lambda X, getting out of your R. This is injection exact for principal ideal S. This means second fundamental sequence of differentials. You get S over S square goes to, so A go F df tensor 1 omega lambda X over lambda tensor R goes down to omega R over lambda goes to 0 exact. So this is no, I made some error. Yeah, this is fine. Yeah. So lambda bracket X over S is R, right? So this is R, and this is R free module. Essentially, and you go down here, so that means there's a one dimension rank 1 thing. So the omega R over lambda is R modulo something, the image of ds LP LP is ds. Okay, so this is a periodic L function. I have still time. So this is basically the end of the story, but I just add some remarks. So under this local complete intersection assumption, you get a periodic L function. That should be, I mean, this idea, oh, there's only 2. Where I put my eraser? It's okay. Oh, this one, yeah. So the first cyclicity theorem tells you that this is just R modulo some idea. If this guy is really generated by 2 or more elements, you would have real trouble. I mean, this Iwasawa's philosophy is that this has to be a periodic L function, at most up to finite error kind of thing. So so unless you assume something good property of R, for generalized, of course, not at all true. So this kind of local complete intersection or Gorenstein kind of things necessary. However, for the Hecke algebra side concerned, there's a lot of non-Gorenstein examples. When epsilon bar is delta bar kind of things happens, or reducible low bar case non-Gorenstein thing occurs. And in this case, there are infinitely many such examples. So this is also something, if you can prove in this Iwasawa theory type of things up to finite error, that is far more difficult to prove exact identity. And exact identity kind of things, the real reason, and the finite error type of looks weaker result. The things in behind is perhaps different. Yeah. So making things up to finite error gives you a lot of error. Okay, that's one thing. And so I have still some time. I asked the question that starting from R, that is P, and for what P Sarma add say RP is cyclic, and the annihilator generated by one element. So this is a two cyclicity. This module is cyclic, and the annihilator also cyclic, I mean principal. So that's kind of question I asked at the very beginning. And of course, higher weight case, it's sort of trivial, as I explained. However, actually cyclicity, I can prove that P doesn't divide ramification index of P in F rho bar over Q. And in this case, it's still cyclicity is true. And for a given compatible system, this perhaps occurs very rarely. But still okay. So perhaps if the adjoint, so trivial case is because the adjoint L value, higher weight trivial means adjoint L value is prime to P, and therefore Selma group is 0. So you try to do that for adjoint Selma group is non-trivial. That means adjoint L value is non-trivial. And then under this companion form case, it's okay somehow. So it is very much related to this companion problem, like local intercomposability and so on. So that's interesting point. This is one thing. So, and second thing is that, as I said, that when F is, you start of Q square root of D, now D positive, and that I call it, say, K, then you start from Artin representation R induced from F to Q of phi kind of thing. Then what you can prove is that, so for simplicity, I suppose that order of phi is prime to P. So this is basically your image Galois group has order prime to P. So this is very close to P doesn't divide G3. And then Selma group of add rho is something like T modulo theta, and if P doesn't divide HK further. So theta is that L, and theta, and also under T is lambda generated by theta. So that's the guy which gives actually the presentation. And further you choose theta well, then theta is a root of an Eisenstein polynomial I say E of x. So I'm writing T is lambda bracket x, bracket S, and S T. T is sent to theta here, and S x, you have a distinguished polynomial e of x and unit polynomial u of x in lambda bracket x, right? And this is a distinguished guy, but you can prove that this is an Eisenstein polynomial. So T is isomorphic to lambda over now polynomial ring over Ex, and this is irreducible. What kind of Eisenstein polynomial modulo? Actually, so this K has fundamental unit, say epsilon, and you embed this epsilon into lambda the following way. Lambda is W double bracket T, and so I write epsilon to be the image, so it's small t to the log of epsilon, periodic logarithm, divided by log of generator, say 1 plus p, kind of thing. Then E0, the constant term, is this epsilon minus 1. So this degree of E, I proved up to here really correctly, but this degree E is twice of some E. And in a paper posted in my web, I claim that E is equal 1. So this is still question. I found some error there. So I'm trying to fix it. So you don't believe this part of the theorem, but up to here is okay. So it is Eisenstein polynomial with respect to prime factor of this one. And this, of course, T itself divides epsilon minus 1, obviously. And this is square free. And theta is therefore the adjoint L is the LP is what? It is just a different, LP generates the different of this Eisenstein polynomial. So that is actually twice E times theta times twice E minus 1. When E is 1, it is just 2 times theta. 2 is a unit, so I don't care. But so this is the thing. And so I know basically almost everything except for this one. And in this case, as you see, this is all the time non-unit. Therefore, this is all the time non-unit. It's further the power up possibly. And therefore, Selmer group is all the time infinite. Okay, so that's one thing. I still have 5 minutes. Now the last question is the question of Beck-Carré. Asked that a full universal deformation ring so when full universal deformation ring of RP is regular. Full means that you don't impose ordinality. It just unramified essentially outside P. So it's a 3 variable, essentially dimension falling. So the over lambda, it is 3 variable at least it has. And they conjecture that except for finitely many or something. And they also wanted to do this for ordinary thing, the same thing. But by this example, the real quadratic case, the ordinary case, so this R I'm looking at, so when R is isomorphic to W double bracket something X, question. And this is a lambda algebra. I'm not saying this lambda is equal to R. If they are equal, the differential will be 0 and Selma group is 0. But in this case, it's all the time non-trivial, so it is real extension. And by this expression using Eisenstein polynomial, right, Eisenstein polynomial, modulo Eisenstein polynomial, this kind of ring is regular if and only if this guy prime factor, this is just a prime. This guy is, of course, you know, the square free and the product of prime. So if E is 1, I could prove I will have a semi-simplicity also. But this is still a question. But this is square free. So what that means, so in the induced case, phi case, the regularity is equivalent to saying that number of prime factors of epsilon minus 1 equal 1. That means epsilon minus 1 is T. Okay? Because this is T to the some power minus 1. Therefore, it's just a cyclotomic polynomial, essentially, the prime is. What does this mean? This is equivalent to saying that epsilon p minus 1. So prime p is factored in p prime in K, right? In the real quadratic field for ordinality condition. And therefore, if you raise, so I fix this p to correspond to my embedding to qp bar, then you raise the splitting prime, so you raise a power p minus 1. This is congruent to 1 modulo cosec p, right? And that's the reason that this is a non-unit. And this is equivalent to saying that modulo p square. And when this happens, for example, you know, for q square root of 5, you can easily compute this by using Fibonacci thing, right? Fibonacci number is essentially epsilon L half of 1 plus 2, 5 or something like that. Epsilon n plus 1 minus epsilon n, epsilon conjugate n plus 1 over epsilon minus epsilon n is a Fibonacci n thing, right? And by this, you can easily compute that. And those prime, so P splitting under this condition and also satisfying this condition is called Wall-Sansom primes. This is a famous prime, the Y Wall-Sansom. The sun is, this is this is, no, this is, perhaps you know, I don't know. Sanzi Wei, Nanjing professor, identical twin. And in the 1992, I think, they wrote a paper, it's before virus. If Fermat's last theorem fails, the first case fails, then it is this prime. Of course, it's not a if and only if thing, but that time very sensational. And people computed this, and no wall Sansan prime, no wall Sansan prime, up to, I think, 9.6 times 10 to the 17 or something. However, you do for other field, not square root of 5, then you lose the connection to Fermat's last theorem kind of thing. But still you can define this condition. Then very many. And the analytic number theorists conjecture that there should be infinitely many, but density 0. But somehow, strangely, you can't find things in Q square root of 5. And why? I don't know. But Fermat's last theorem is anyway true. So I don't know. But this Daniel Wall is an American mathematician. In Faria, he did something for this kind of thing. Okay, so that's it. Thank you. This Selman group non-zero. I mean, this quadratic case all the time non-zero. And of course, in the imaginary quadratic case, if P divides cat's periodic square of some weight coming from this character, finite order character phi, then it is the case. So if P divides cat's periodic square, then it is an induced representation, even higher weight. That is congruent to some Artin representation at weight 1. And that one gives examples. So in this case, I said this theta is something like epsilon minus 1. You replace this bracket epsilon minus 1 by cat's periodic square. Basically, things are true, but I don't know cat's periodic square is square free or not. If it is square free, then this Eisenstein and so on. For the non-CM part, it works. But that's, I don't know. I mean, that's a big conjecture, right? I mean, just a simplicity of some sort of your summer module. So that's, I don't know. So that case. So I don't know on the icosahedral, tetrahedral, octahedral case, there's an example or not. But I think if you move P, then at some point you hit some case when this T getting bigger than lambda, then the Selman group is big. I don't think that for the icosahedral case, you move around P, it is all the time lambda. Perhaps not true. Yes. Yeah. However, my anticyclotomic cyclicity does not assume that P doesn't divide HF. H of quadratic field. So my assumption, this HF in this induced kind of case is that HQ square root of D and H splitting field of phi thing product essentially, because this is quadratic and this is sort of but so P doesn't divide. This means this proof without using this funny Taylor-Wiles system exclude. I can do also HQ square root of D. And this case, I really need this complicated Taylor-Wiles system. So it's slightly anticyclotomic cyclicity things is more deeper. So the real quadratic case also I can do in that way, but in my paper in the Iwasawa volume 2017 and so on, I didn't do that because this is rather awful. And, though Iwasawa 2017, I explained the Taylor-Wiles system. And it's most people doesn't like Taylor-Wiles system, and I like it. But so yeah. But no, under the assumption of cyclicity theorem, I think it is local complete intersection. I mean, if I plug in all this progress of Jackton, Shekhar-Kare, and Kalyan-Swamy, and so on, perhaps it tells that. So if that assumption fails, that means P distinguishes delta bar not equal to epsilon bar thing, then it is non-Gorenstein, therefore non-local complete intersection. It is one variable periodical function specialized to weight one. I mean, this LP is element in T. This LP is element in capital T, and this covers all weight. Therefore, it is exactly one variable guy. But two variable things has exceptional zero along that line. And that residue should be, that derivative should be this one. But that, I think, it's basically proved by Dasgupta, I think. But I forgot the exact assumption he made. So it's mostly known, but it's a derivative thing. Because adjoint L has Frobenius eigenvalue 1 in the middle. That causes this exceptional zero. Thank you.